Welcome back. So the last time we proved the chain rule. Let's continue with the chain rule for now. We'll do some more examples where the chain rule is applicable. But prior to that, let me just recall one theorem that we looked at earlier, but we will just look at it once again because it's an important little result. Yeah. So this is the mean value theorem, the analog of the Lagrange's mean value theorem. So let U be an open set and A comma B in U be points such that this line segment for all t in 0, 1 lies in U. Let f from U to R be a differentiable function then f of A minus f of B is indeed the derivative at some point A minus B for some theta in 0, 1. This is the analog of Lagrange's mean value theorem in multivariable calculus. So what does Lagrange's mean value theorem state? It states f of A minus f of B is the derivative at some point in between times A minus B, right? That would be the one variable calculus version. It's very similar here. Instead of derivative at, what we really mean is the gradient, but evaluated at some point in between. When we say some point in between, we mean that if you take a straight line joining A and B, it's at some point on the straight line, right? So we assume that this entire straight line lies in the domain. This is crucial. And by saying the derivative times, what we really mean is the dot product of the gradient with this vector, right? So it looks a little formidable, but its proof is rather straightforward. So suppose you take this one variable function g of t. We already looked at a version of this sort of a thing earlier. Nonetheless, so on 0, 1, by the chain rule, you don't really need the chain rule, the full strength of the chain rule here. This is much more elementary, but might as well use it. G is differentiable and hence continuous. Differentiable on 0, 1 and continuous. In fact, it's differentiable not just on 0, 1, but on the closed interval no less. Why is this so, right? The point is A and B are within an open set, right? So there is a small ball around A, small ball around B. So you can extend this line segment a little bit beyond A and B. So in fact, we can say it's differentiable on minus epsilon, comma 1 plus epsilon for some epsilon positive. Yeah? And it's continuous on this. Why is it continuous? Because it's differentiable. Now, what we can do is we can differentiate this. What is the derivative of this? Once again, it's the derivative of f at this point and the derivative of this function, which is simply the vector A minus B. In other words, it's basically the gradient evaluated at this point times A minus B. Now, by the usual Lagrange's mean value theorem, g of 1 minus g of 0 is g dash of theta for some theta times 1 minus 0. So right, for some theta. So it's very easy to prove it just by using the usual Lagrange's mean value theorem. There is a small technicality, of course, over here, but that's not too big a deal. Okay. So other than that, it's actually very straightforward to prove this theorem. One caveat here, a very important cautionary point. This theorem is false for vector valued functions. So this theorem is not true for vector valued functions. This is a very important point to note, right? Why would you expect it not to be true for vector valued functions? The point is, of course, you would argue that why not use this theorem for each component of a vector valued function. That is perfectly reasonable, of course. The trouble is, when you use it on each component, the theta that you get here will depend on the component. It can vary from component to component. So a single theta may not work. Okay? That's the reason why you cannot expect it to be true, but not expecting something versus it being false, they're two different things. So you need to come up with a counter example. If you do not manage to come up with a counter example, then you must suspect that it could very well be true, right? So for example, let's take t in 0 2 pi to cos t comma sin t. In fact, not t in 0 2 pi, t in all of r cos t comma sin t, right? So let's call this f of t. F of 2 pi minus f of 0 is what? It's cos of 2 pi comma sin of 2 pi minus cos 0 sin 0. What's this? Cos 2 pi minus cos 0 is 0, sin 2 pi minus sin 0 is 0. This must apparently be, since it's supposedly, it is f dash of theta times 2 pi minus 0, apparently, supposedly. If it were true, if LMVT were true, what is the derivative of this? It's minus sin theta and cos theta times 2 pi, which means sin theta is 0 and cos theta is 0, but this is impossible because sin square theta plus cos square theta must add up to be 1. Okay? So that's the problem. So this Lagrange's mean value theorem business in multivariable calculus only holds for scalar valued functions. For vector valued functions, you can use it one component at a time, provided you note that the theta that you get will depend from component, will vary from component to component. Okay? Anyway, let's do some more examples of the chain rule. So recall this point in one variable calculus. One of the points of the chain rule in one variable calculus was to compute the derivative of sine inverse of x, right? So if sine inverse of x is assumed to be differentiable, first of all, we have to be careful here. Sine is not an invertible function if you take its domain to be all of R, right? It's periodic. Its graph looks like this, right? So, so that's the problem. Since it's periodic, it's not really invertible. But if you restrict its domain to, let us say, for example, this piece, right? So if you pretend that sine is defined not on all of R, but say, for instance, between minus pi by 2 and pi by 2. Right, suppose you assume this is the case. Well, here it is surely 1 to 1, right? If you go beyond it, either in this direction or in this direction, you're in trouble. But in this domain, it's certainly 1 to 1. So sine, you certainly get something that, I mean, this is, sorry, from minus pi by 2 to pi by 2. This is sine x. Surely its inverse exists. Okay, because it's 1 to 1. Right. So if you assume sine inverse of x is differentiable at a point, it's not obvious that it's differentiable. Then how do you compute its derivative? Well, you say that what is sine inverse of x? After all, it satisfies this. So by the chain rule, one variable chain rule, you say cos of sine inverse of x times sine inverse of x. The derivative is 1. So sine inverse of x, the derivative is 1 divided by cos of sine inverse of x. What is cos of sine inverse of x, right? Well, suppose we are in the right region. Suppose it's sine inverse of x square, and you want to say it's this, because sine of sine inverse is just x itself. You have to be a tad bit careful, because actually cos square something plus sine square something is 1, but cos can then be potentially plus minus of this, right? So at least in a certain region this is true, right? Okay, assume that this is equal to this. So we don't care about these technicalities for now. The real point I'm trying to make here is using, if you assume that a function is different, inverse of a function is differentiable, you can use the chain rule to actually calculate the derivative of the inverse. So that is what I'm trying to head to. So here is a little proposition. So here is a small little proposition. Let f from U in Rn to Rn be differentiable at an interior point A in U. Okay. Right. Suppose the inverse f of A, where does f of A lie in? Is an interior point of f of U. Sometimes it's easier to use a shorthand notation. So suppose f of A is an interior point of f of U, and f from V to f of V, I'll just draw a picture in a moment, where V is a neighborhood of A, is 1 to 1, onto, obviously it's onto, right? F of V is open, and f inverse from f of V to V. So obviously if f is 1 to 1 from V to f of V, f inverse makes sense. The other hypothesis we are making is this is open. This is a hypothesis. F inverse from f of V to V is differentiable at f of A. So these are all hypotheses. Then df A is invertible, and we have a formula for the derivative of the inverse at the point f of A. Okay, it's the derivative of f at A inverse. Okay, when I say inverse, I mean matrix inverse. See, the inverse sign can be very confusing at points, because do I mean the inverse as a function? Do I mean it as a matrix, and so on and so forth? So I'll try to be as explicit as possible every time. So this formula, while it looks rather complicated, is to be expected. After all, what did we do here, right? When we did this, the derivative of the inverse is simply 1 divided by the derivative of the original function. Okay, so it's the reciprocal of the derivative of the original function. For matrices, reciprocal doesn't make sense, so we take the matrix inverse. Okay. So as a consequence, we are also asserting that the derivative matrix is an invertible matrix. Yeah. Later on, much later, we will see something called the inverse function theorem, which is in a sense a converse of this result. That is, if the derivative matrix is invertible, then all these hypotheses hold and the derivative of the inverse turns out to be given by this formula. So the inverse function theorem will later on tell us when a function, the inverse is actually differentiable. Notice, let me just spend a couple of minutes on this proposition. So if I take u and if I take a, this is an interior point, right? And it goes to f of a, and this u itself would go to some f of u. This is an interior point of f of u, this is an interior point of u. This is the assumption. Not only that, we can choose an open set V here so that the image f of V is also open. This is an assumption. This is 1-to-1, and this inverse we are assuming is differentiable. So notice this is a local inverse. When I say the word local, what I mean is we are looking at neighborhoods of points. We are not looking at the entire domain itself, right? I mean, we are looking, say, within, say, Bangalore, not within all of India. That's the analog of what I mean. So if I have so this proposition can be stated in fewer words as: assume that f is locally invertible near the point A, and it's locally an open map. That is, there exists a neighborhood V of A so that f of V is open. And assume that the local inverse is differentiable. That means this inverse is only makes sense in a small region around f of A. Then the derivative at A is invertible, and the derivative of the inverse is given by something. Okay. Okay, so the statement of this theorem requires more work than its proof. The proof is very straightforward. F of f inverse of x is x. So by the chain rule, the derivative of f at the point A times the derivative of f inverse at the point f of A is identity, which means df is an invertible matrix, and its inverse, and the inverse of this invertible matrix is indeed the derivative of this. Right? Maybe it's easier to say, instead of this, f inverse of f of x equals x. Maybe this is a bit easier. So the derivative of f inverse at f of a times the derivative of f at a is identity. Maybe that's a little easier. Nonetheless, so we get the conclusion rather quickly. Where then did we use all these hypotheses? We obviously need f inverse to be defined, and we need it to be differentiable. That much is fine. Where are we using the fact that f of v is an open set? right? The key point here is differentiability makes sense only on open sets, at least the way we have made sense of it. So for the derivative of f inverse, so to say that f inverse is differentiable at f of a would entail f of a to be an interior point, okay? But we need a bit more than that. We need the ability to use the chain rule, which means we would want f inverse to be defined on an open set and to be defined on an open set containing the image of f of x, right, of f. So that's why we need all these hypotheses, right? Okay, so we will return to this a little later when we deal with the inverse function theorem. Here are some more examples of the chain rule if you wish. So suppose you have a path. What is a path? Well, a path is, let's take an open interval, is simply a function from R to this, and so we usually say differentiable path, meaning this is a differentiable function. Okay, so a path is simply a function from R to Rn. Sometimes we will make a distinction between curve, which is the image of the path, which is this geometric object in Rn. So a curve is typically treated as a subset of Rn, whereas a path is typically a function. But we will use these terms interchangeably. Okay, but nonetheless, the technical terms are as follows. So suppose if a path is regular. What is regular? Regular is defined to be the derivative of t being non-zero for all t in the domain. Okay. Then this particular thing is sometimes, not always, but some people like calling this the directional derivative of f along this path. Okay, sometimes this is written as df ds. Okay, so the directional derivative of f along this path is simply taking the direction of the path, which is the velocity divided by the speed, so that you get the a vector of magnitude 1, and then taking this. Okay, so it is indeed the directional derivative along this path, right? It's a perfectly reasonable definition. But for us to be able to divide by the derivative's magnitude, we want the derivative to be non-zero. Okay, right. Okay, so we can for instance do this in a particular example. So if for instance f of x comma y is, let's say, x square minus 3xy, and let's say the path is this, right? This is obviously differentiable. This is differentiable. Why are these so obviously differentiable? These are one variable functions. They're polynomials, and this is also a polynomial. Polynomials are differentiable, right? So by the chain rule, df dt, df, I'm not quite using the chain rule yet. Suppose I want to compute this. Right? This is not quite an application of the chain rule unless I interpret this symbol carefully, which I'm not right now. Okay, so why am I writing it as df ds? That's a longer story, but for now let's just treat it as a symbol. right? So the first thing to note is this path a regular path? Sure it is, because this is never 0, 0, right? So by definition, the symbol is simply the gradient of f times the velocity divided by the speed, right? What is the gradient of f? The gradient of f is a vector. It's df by dx, which is 2x minus 3y, and df by dy, which is 2 minus 3x. So this is simply this vector dot the speed, if you will, 1 plus 4t minus 1 square, right? So it is 2x minus 3y plus minus 3x times 2t minus 2 divided by this. Now we want to substitute t equals 1 here. So it's, what is x here? So when t equals 1, r of 1 is 1 comma 1 minus 2 plus 2. So this is simply 1 comma 1, right? So this is simply 2 minus 3 times 0 divided by 1. Okay, so it's simply equal to it's simply equal to minus 1. Yeah. Right. So this is a rather straightforward calculation. Yeah. So that proves that. So here's one more example. So the previous example was not really an application of the chain rule unless you interpret the symbol df by ds correctly, yeah, which we have not done, but which we will soon enough, right? Okay, so suppose f of xy is x square minus y square, and you have two paths. Right? What's the gradient of f? It's 2x and minus 2y. What are the derivatives of these paths? It's 1 comma 2. This one is 2 comma 4. And neither is 0, 0. So both paths are regular paths. Anyway, what is df dt? Using the first path, let's not call them df dt. Let's be more precise. Let's say g1 of t is f of r1 of t, and let's say g2 of t is f of r2 of t. So what's g1 dash? By the chain rule, it's the gradient of f at r1 of t times the derivative of r1 of t, which is what, right? It is 2x comma minus 2y, right? So this is the dot product, so we might as well just say this. So it is 2x minus 4y, which is, what is x? X is t. What is y? Y is 2t, right? So it is minus 6t, right? Now suppose we play the same game for g2. What will we get? So g2 rather than, so what will we get? We will, okay, might as well just, so this would be right. So this part is still going to be the same. This will vary. This will be twice of 1 comma 2. Okay. So you might think it's just twice of this, but actually x and y are also twice of their original value. So this will be 4 times the original value, right? This is not equal to g1 dash. So this is a problem, because if you look at the curves of these two, both of them are the same geometric object, but we have parameterize them differently. In other words, we have a particle moving at different speeds along the same geometric object, right? So it will of course see the this function changing at different rates, right? That is the problem. Now if you compute df dg1 ds and dg2 ds, right, these two will agree if you choose things correctly, right? So we need to interpret, of course, what d by ds means, right? Is something really a function of s, or are we just using it as a symbol, right? Anyway, we'll continue with this the next time. So for now, let's stop. Thank you for joining.